It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good morning, everybody. Welcome to Tibbetts Physics. What is crappin'? Today we are going to do chapters 10, 11, and 12 practice problems, all from thermodynamics. Number 1. The temperature gradient between the skin and the air is regulated by cutaneous blood flow. If the cutaneous blood vessels are constricted, the skin temperature and the temperature of the environment will be about the same. When the vessels are dilated, more blood is brought to the surface. Suppose during dilation, the skin warms from 72 degrees Fahrenheit to 84 degrees Fahrenheit. Letter A. Convert the temperature to Celsius and find the difference. So we're going from Fahrenheit to Celsius. We'll use the formula, which is the temperature in Celsius, we'll label it as T sub C, is 5/9 times the temperature in Fahrenheit minus 32. So all we have to do is plug and chug for both of them. Let's show our work for the first one. The temperature in Celsius is 5/9 times 72 degrees Fahrenheit minus 32. And that gives us a temperature in Celsius to equal 22.2 degrees Celsius. We'll call it Tc sub 1. If we do the same at 84 degrees Celsius, we get a temperature to equal 28.9 degrees Celsius. And the second part of the question is to find the difference. So we'll find the change in temperature. That's the final minus initial. So the change in temperature in degrees Celsius will be Tc2 minus Tc1, and that gives us 6.7 degrees Celsius. Letter B asks us now to go from degrees Celsius to kelvins and also find the difference. So all we have to do to go from degrees Celsius to kelvins is just add 273. So TK1, the temperature of the first point in kelvins, will equal TC1 plus 273. And that gives us 295.2 kelvins. TK2 is 273 plus 28.9 degrees Celsius, and that gives us 301.9 kelvins. We also want to find the change in temperature, and we'll get the same thing. The change in temperature in kelvins will equal 6.7 kelvins. Number 2, a steel railroad track has a length of 30.000 meters when the temperature is 0 degrees Celsius. What is the length on a hot day when the temperature is 40.0 degrees Celsius? What about on a cold day when the temperature is negative 10 degrees Celsius? And we're told the coefficient of linear expansion for steel is 11 times 10 to the negative 6 per degree Celsius. So let's label our knowns. The initial length, we're told, is 30.000 meters. The initial temperature, T sub I, is 0 degrees Celsius. The final temperature for letter A, we could say, is 40 degrees Celsius. And the coefficient of linear expansion, that's going to equal E alpha, 11 times 10 to the negative 6 per degree Celsius. And what we want to find is the final length. How much did the track expand? For this type of problem, because the coefficient of linear expansion is in degrees Celsius, we're going to keep our temperature in degrees Celsius. So we won't convert to Kelvins. I'm going to call letter A solving for the linear expansion when it heats up to 40 degrees Celsius. The formula for that is L sub F equals L sub I plus alpha L sub I delta T. And we know everything in this problem, so all we have to do is plug and chug. L sub F equals 30.000 meters plus 11 times 10 to the negative 6 per degree Celsius times, again, the initial length, 30.000 centimeters. Just kidding, meters. Not quite sure why I said centimeters. Meters times the change in temperature, which would be 40 degrees Celsius minus 0 degrees Celsius. Plug in chug, and we get a final length to equal 30.013 meters. Letter B, we want to solve for the same thing, the final length, except this time, when it, we'll say when it starts out at 0 degrees, when it starts out at 40 degrees and it's cooled off to negative 10 degrees Celsius. So the change in temperature for this problem would be negative 10 degrees Celsius minus 40 degrees Celsius, which gives us negative 50 degrees Celsius. So we can plug this into the same formula, and we get a final length, L sub F to equal 29.997 meters. So when it cooled off, it's going to shrink, and it's going to shrink before its initial length compared to when it was at 0 degrees Celsius. All right, number 3. A circular copper ring at 20 degrees Celsius has a hole with an area of 9.980 centimeters squared. What minimum temperature must it have so that it can be slipped into a steel rod having a cross-sectional area of 10.00 centimeters cubed? So we could say that the initial area of the copper ring is 9.980 centimeters cubed. And we want it to expand to 10.00 centimeters cubed so it could fit inside it. Centimeters squared, I'm sorry. We know that the initial temperature is 20.0 degrees Celsius. We want to find what the final temperature is, so how much we have to heat it up to cause it to expand. And if we look in our reference tables or in our textbook, we're told that gamma, the area coefficient of expansion, is equal to 34 times 10 to the negative 6 per degree Celsius, and that's for copper. Similar formula for the linear expansion. A sub F is equal to A sub I plus gamma A sub I delta T. Let's expand delta T, and let's just subtract A sub I over to do a couple things at once. So A sub F minus A sub I equals A sub I times the final temperature minus the initial temperature. We want to solve for the final temperature. So we'll divide by gamma A sub I, A sub F minus A sub I over gamma A sub I, and then add T sub I to the other side. So plus the initial temperature. And that gives us the final temperature. So let's plug and chug. 10.000 centimeters squared minus 9.980 centimeters squared all over 34 times 10 to the negative 6 per degree Celsius times A sub I, 9.980 centimeters squared, plus the initial temperature, 20.0 degrees Celsius. Plug and chug, and we get a final temperature to equal 79 degrees Celsius. Next question. This slides up. Next question, number 4. An ideal gas at 20 degrees Celsius and a pressure of 1.50 times 10 to the 5th pascals is in a container having a volume of 1.00 liters. Letter A, determine the number of moles of gas in the container. Let's start with what we know. The temperature is 20.0 degrees Celsius. The pressure, 1.50 times 10 to the 5th pascals. And the volume is 1.00 liters. We can also look up R, Rydberg's constant. And we have 2 of them. We want to use the one that is a result of our pressure being in pascals. And that's 8.31 joules per mole times Kelvin. Since we have a Kelvin here, we have to convert our temperature to kelvins. So we're going from degrees Celsius to kelvins by just adding 273. So the temperature equals 293 kelvins. And we're finding N, the number of moles. We're going to use the formula for letter A, PV equals nRT. And all we have to do is just isolate N, the number of moles. So let's divide by RT. N equals PV over RT. And from here we just plug and chug. N equals 1.50 times 10 to the 5th pascals I forgot to mention we also need to convert our volume to meters cubed. So 1 liter is 1.00 times 10 to the negative 3 meters cubed. Sorry about that. 1.00 times 10 to the negative 3 meters cubed. All over R, 8.31 joules per mole times Kelvin, times the temperature, 293 kelvins. Plug and chug, and we get the number of moles to equal 0.0616 moles. Part B, The gas pushes against a piston, expanding it to twice its original volume, while the pressure falls to atmospheric pressure 1.01 times 10 to the 5th pascals. Find the final temperature. Let's start with PV equals nRT again. And let's solve for the temperature. T equals PV over nR. T equals, the new pressure is 1.01 times 10 to the 5th pascals, times the volume doubled, so we'll put 2.00 times 10 to the negative 3 meters cubed, all over, and the number of moles, that's 0.0616, times R, 8.31 joules per mole times Kelvin. Plug in chug, and we get a temperature to equal 395 kelvins. We could have also solved for letter B by setting up a proportion. And we could have said that Pi, or P1, V1 over T1 would equal to P2, V2 over T2. If we didn't know the number of moles, we could have solved it using this method, and we would have gotten the same answer, 395 kelvins. Number 5. A steel strut near a ship's furnace is 2.00 meters long, with a mass of 1.5 kilograms, and a cross-sectional area of 1.00 times 10 to the negative 4th meters squared. During operation of the furnace, the strut absorbs a net thermal energy of 2.50 times 10 to the 5th joules. Steel has a specific heat of 448 joules per kilogram times degrees Celsius. Letter A, find the change in temperature of the strut. Let's start off by writing down our knowns. The initial length is 2.00 meters. The mass, 1.57 kilograms. And a cross-sectional area, 1.00 times 10 to the negative 4th meters squared. It absorbs a net thermal energy. That's Q. It's not internal energy like we've been using in Regents physics. Q stands for thermal energy at the college level. Q equals 2.50 times 10 to the 5th joules. And it has a specific heat, which is C, 448 joules per kilogram times degrees Celsius. So finally, let's look at letter A. Calculate the change in temperature of the strut. Delta T equals question mark. The formula we use is Q equals MC delta T. The specific heat formula. All we're doing is solving for delta T. Delta T equals Q all over MC. Then we just plug and chug. 2.50 times 10 to the 5th joules all over the mass, 1.57 kilograms, times C, the specific heat, 448 joules per kilogram times degrees Celsius. Plug and chug, and we get a change of temperature to equal 355 degrees Celsius. Letter B, find the increase in the length of the strut. let's find what its final length is as a result of its temperature increasing by 355 degrees Celsius. We're looking at a steel strut. We can look up alpha. Its its coefficient of linear expansion, alpha, which is 11 times 10 to the negative 6 per degree Celsius. The coefficient of linear expansion. We're finding the final length. We're going to go back to the formula we used before for linear expansion, linear thermal expansion. L sub F equals L sub I plus alpha Li delta T. And all we have to do is plug and chug because we're just solving for LF. 2.00 meters plus 11 times 10 to the negative 6 per degree Celsius times 2.00 meters. And then the change in temperature, 355 degrees Celsius. Plug in our calculators and we get a final length to equal 2.00781 meters. Next question, number 6. Number 6. An ideal gas absorbs 5.00 times 10 to the 3 joules of energy while doing 2.00 times 10 to the 3 joules of work on the environment during a constant pressure process. Compute the change in the internal energy of this gas. It's absorbing 5, which is Q, the heat, 5.00 times 10 to the 3 joules. And the work is being done by the system on the environment. That work is going to be negative because it's by the system on the environment. That'll be negative 2.00 times 10 to the 3 joules. And what we want to find is the change in internal energy, which is E therm. So we'll use the formula Q equals, change in E therm equals, change in E therm equals Q plus W. And this W is the work that's being done on the system by the environment. We're negating it here because it's being done by the system on the environment. So the system is doing the work, which makes it a negative W. We can just plug and chug, change in E therm equals 5.00 times 10 to the 3 joules plus negative 2.00 times 10 to the 3 joules. That gives us a change in internal energy to equal 3.00 times 10 to the 3 joules. The tricky part with these questions is our negative signs. And when work is being done by the system, we have to negate it. When work is being done on the system by the environment, it stays positive. Letter B. If the internal energy now drops by 4.50 times 10 to the 3 joules, and 7.50 times 10 to the 3 joules of energy is expelled from the system, find the change in volume assuming a constant pressure process at 1.01 times 10 to the 5th pascals. We're told the change in internal energy, because it drops, it'll be negative 4.50 times 10 to the 3 joules. And 7.50 times 10 to the 3 joules of, we say, heat energy is expelled from the system. that means it's going to the environment, which means it has to be negative because it's leaving the system. Negative 7.50 times 10 to the 3 joules. And we want to find the change in volume as a result of this when the pressure is 1.01 times 10 to the 5th pascals. We'll start with the same formula. Change in E therm is equal to Q plus W. Change in E therm is equal to Q. W is work, which is equal to negative force times distance. Write that down. W equals negative FD, which equals negative the pressure times the change in volume. So now we can put Q minus P delta V. We're solving for delta V, so why don't we subtract Q and divide by negative P. Delta V equals change in internal energy minus heat all over negative the pressure. And from here we can plug and chug. Change in volume equals negative 4.50 times 10 to the 3rd joules minus negative 7.50 times 10 to the 3rd joules all over negative P, so negative 1.01 times 10 to the 5th pascals. Be careful with your negative signs in your calculator, but we plug and chug and we get a change in volume to equal negative 2.97 times 10 to the 3rd meters cubed. Last question, number 7. During one cycle, an engine extracts 2.00 times 10 to the 3 joules of energy from a hot reservoir and transfers 1.50 times 10 to the 3 joules to a cold reservoir. Letter A, find the thermal energy efficiency of the engine. We're given that Q hot is 2 times 10 to the 3 and Q cold is 1.50 times 10 to the 3 joules. Letter A asks, find the efficiency of the engine. One of the formulas we have for efficiency is the absolute value of Q hot minus the absolute value of Q cold all over Q hot. All we have to do is plug and chug, so 2 times 10 to the 3 joules minus 1.50 times 10 to the 3 joules all over 2.00 times 10 to the 3 joules. Joules. Plug and chug and we get 0.250. And if we want to put that as a percent, we can just multiply by 100, which says that this engine is 25% efficient. Letter B, how much work does this engine do in one cycle? Work is just the absolute value of Q hot minus Q cold. So W is Q sub H minus Q sub C. 2.50 times 10 to the 3 joules minus 1.50 times 10 to the 3 joules. That gives us work to equal 500 joules of energy. And the last part, letter C, what average power does the engine generate if it goes through 4 cycles in 2.50 seconds? We know that power is equal to work over time. So we just plug and chug, but 500 joules is for one cycle. To do 4 cycles, we'll multiply by 4. 4 times 500 joules, all over 2.5 seconds. Plug and chug, and we get 800 watts of power. That's it for this video. I hope you found these problems useful. Thanks for watching, and I'll see you next time. See ya!